This is a little lecture on the Doppler effect. Part of it I'm going to show you a simulation, and I'll send you the link to the simulation as well if you want to play with it yourself. I also really encourage you, if you haven't watched the first two videos that have an example of the Doppler effect, to go listen to those first so that you really thinking about here. If you have watched those videos, then you will have definitely noticed something in the sounds that you heard of the various sirens in the videos. And what you should have noticed was a change in the pitch of the sound. Now, keep in mind pretty carefully that I'm talking about the pitch here, not how loud it is. So think about the note. It goes from high to low. Not the fact that it changes its volume. It does that too, but that's completely... What I'm talking about here is that change in the pitch. Now you should remember from class that when we're talking about the pitch of a sound wave, that has something to do with the frequency. And the Doppler effect you're going to see is defined to be a shift in the wavelength and the frequency of a wave. And that happens when the source of the waves is either moving towards the observer or away from the observer. It won't happen if it's moving sort of sideways to the observer, but if it's moving towards or away from the observer, we get a change. And so I'm going to switch to the simulation now and just kind of show you a little bit about why this shift happens. So here I am, and this thing that you can see here is making waves with a pretty constant frequency. And you could measure the wavelength, you could pause it, measure the wavelength, you'd see it's the same everywhere on the screen. But now I'm going to start moving it. I'm going to start moving the source of the waves. It's going to move from one side of the screen towards the other. So now it's moving to the right. And then I'm going to let it go back. I should pause it is what I need to do. So as you can see, when it's moving from one side to the other, the side that it's moving towards, the waves are getting kind of bunched up, as you can see over here. And on the side that it's moving away from, they get more spread out. So if we're talking about the wavelength is shorter here, and the wavelength is longer here. So the wavelength is shorter here, that means there's a higher frequency. The wavelength is longer here, and that's a lower frequency. Why is this happening? Well, you can see that the source is sort of catching up to its own waves as it moves along. As it moves along, it catches up to its own waves. And so it has moved part of the wavelength by the time it emits the next crest of the wave. So that's why it's getting shorter. And it's moved more than the wavelength away when on the other side, by the time that it gives off the next one, it has moved farther, and so the wavelength is getting stretched out. How much this happens depends on the speed. I can change the speed, make it faster. So now I'm going pretty fast. And so you see it gets very bunched up on the side that it's coming towards and very spread out on the side that it's coming away from. So this shift depends very much on how fast the source is moving. And that's one of the things the Doppler effect is most useful for, is determining the speed of things. For instance, you've probably heard of Doppler weather on the news. And the advantage of having Doppler radar as opposed to just normal radar is that normal radar will tell you where the clouds are. That's a nice thing to know, where the clouds are. But if there's a storm coming towards you, what if there's a tornado or something, you would maybe like to know how fast that storm is moving. When's it going to get to me? So you want to know the speed, and the Doppler effect will tell you the speed. In astronomy, this is useful too, because there are things in space that are moving towards us and things in space that are moving away from us. And so this is how we can even measure the speed of things in space, which is a pretty cool deal. So back to the notes. So when the wave is coming towards you, the wavelength gets shorter. When we're talking about sound, that means you get a higher pitch. When it's moving away from you, the wavelength gets longer, and you have a lower pitch. For light, it's a change in color. That change in wavelength corresponds to a change in color with light, just like it corresponds to a change in pitch with sound. So blue light happens to have shorter wavelength than red light, so when something's coming towards you and it's giving off light, that means its color becomes more blue, and if it's moving away from you, it becomes more red. So we start using these words called blue shift and red shift when we're talking about light. If you take astronomy, that will be a very, very, very important concept. But again, for sound waves, it's a change in pitch. You hear a higher pitch when it's coming towards you. You hear a lower pitch when it's going away from you. Now, this is the formula, and you're going to want to write all this down. What I would suggest you do is pause it, write it down, and then listen to my explanation. This is a three-part equation. There's three things that are all equal to each other in the Doppler effect. One is a set of wavelengths. One is a ratio of two speeds, and one is a single variable by itself. So I'm going to actually start with these, the wavelengths. There's two wavelengths that are involved in the Doppler effect. There's the wavelength that it would be if the source was just sitting still. What the wavelength normally is, what it should be if the source was just sitting still. That is going to be what we call the rest wavelength, rest when it's at rest, when it's not moving. That's going to be what we call lambda naught. So that's a 0, like we had V0, V naught in the first semester. This is what it is when it is at rest, when it has a speed of 0. So that's what it should be. You'll see these kind of words in problems. Lambda is the observed wavelength, what you see because the source is moving. The most common mistake that students make on problems like this is to mix up lambda and lambda naught, so be really careful about that, make sure you know which is which. We also have two speeds involved. There's how fast the source is moving. For instance, in one of the videos you saw an ambulance. In that video, the source was the ambulance. So if we looked at the ambulance's speedometer, what we would get would be Vs. This is one of those things where you're going to have to pick a sign. I'm going to tell you positive, and you're going to have to decide if it should be positive or negative. If it's coming away from you, you're going to make it positive. If the source is coming towards you, you make it negative. And then VW is the speed of the waves. So in the ambulance's case, we had sound waves, and so I want the speed of sound, which is about 340. If it were light waves, we would want the speed of light, which is 3 times 10 to the 8th. Your VW is going to be one of these two numbers in every problem that we do in this class. If it's sound, it's 340. If it's light, it's 3 times 10 to the 8th. And then finally, Z. Z is just a special name for this ratio of the two speeds. When we're talking about sound, it's called the Mach number. For instance, you've heard of an airplane traveling at Mach 3. What that means is that the source is traveling 3 times the speed of sound. So Vs over Vw is 3. That's the Mach number. When we're talking about light, it's called the red shift or the blue shift. And that's a ratio of the speed of the source to the speed of light. That number, Z, will be positive for something that's moving away, something that gets redder, and negative if it's moving towards you and getting bluer. The Mach number has no units because it's like meters per second over meters per second. That cancels. And you can pick any two of the 3 parts of this equation and set them equal to each other. So you could use Z equals lambda minus lambda naught over lambda naught. You could use Z equals Vs over Vw. You could use Vs over Vw equals lambda minus lambda naught over lambda naught. It doesn't matter which 2 parts you pick. Just pick parts based on the information in the problem. I'm going to do another video later that will have several examples of how to do problems involving this math. So that will be coming in a later video.